Lesson 9-9, DC circuits containing resistors and capacitors. This is a capacitor. Capacitor is essentially just two pieces of metal separated by a space in between. And what a capacitor does is it stores charge. So it can be used as a little battery or something like that, only it's not, it doesn't store charge chemically like batteries does. It just stores charge because as the current goes around, it builds up charge on one side, and then that repels those charges from the other side, which makes the current continue on. But that charge builds up there. We're going to charge a capacitor, and we have a circuit like in the diagram with just a capacitor, a battery, and a resistor. Initially, let's say the capacitor is not charged. And the battery is connected, the current flows, and since the electrons are going there, electrons start building up right here in the capacitor. As the charge builds up, there's an increase in resistance because the repulsion of the charges. I mean, there's already charge there. It means more electrons don't really want to go there. When the capacitor is fully charged, no more current will flow. So the need for the battery to send the charges out is balanced by the repulsion force of the charges here at the capacitor, so no more current goes. We use our loop rule. The EMF from here equals Q over C, and that is the volts on a capacitor. The charge on capacitor is Q equals CV, where C is the capacitance. And so the volts is Q over C. And for the resistor, it's V equals IR, so our volts equals current times resistance. So this is the volts of the battery equals the volts being used by the resistor and the capacitor. If I solve that for I, we end up with that. However, that is a current is the rate of change of current here is rate of change of charge. So this is actually called a differential equation, which means calculus has to solve it. So we'll just give you the answer. So charging a capacitor, the charge equals CV. So that's the maximum charge. This is the max charge of the capacitor times 1 minus e to the negative t over RC. Maximum charge. RC we'll call tau, Greek letter tau, is the time constant, and that is the time required to charge the capacitor to 63.2%. And the CV is the maximum charge on the capacitor. If we want it as volts, we could do the same thing, only now we have the volts on the capacitor equals the EMF times that same 1 minus e to the negative t over RC. V is the volts across the capacitor, E is the EMF, T is our time, and R and C give us the time constant.